Welcome back, everybody. In this video, we're going to be working on another class of word problems called uniform motion problems. So the background first and then some examples. So first of all, in all of these problems, we're going to be using the equation d equals r times t. This stands for distance traveled equals the rate at which we're traveling, or the speed, multiplied by the time at which you are traveling. So the rate times time is always equal to the distance. So just a couple of quick examples to make sure that we're okay with that part of it. So first of all, if you were to go 60 miles per hour for 2 hours, it should make sense. 2 times 60 is 120. We would end up going 120 miles. Okay. So there we multiply the 60 times 2, getting 120. Thinking in terms of the units also, we're going 60 miles in every 1 hour, and we're going to multiply that by 2 hours. The units of hours are going to cancel, leaving us an answer that is in minutes. Okay, as another example, suppose that you needed to make a 1,600-mile road trip, and you needed to get it done in 5 days. How fast do you need to go? Okay, distance is 1,600 miles. We're going at an unknown rate r, and we need to get it done in 5 days. Okay, dividing 1,600 by 5. That's our rate. That would be 320 miles every day. You would need to travel 320 miles every day to complete the whole 1,600 miles in 5 days. Okay, so one thing that you noticed probably is that we were going at a constant speed in each of these situations, which is not realistic, but that's the way that it goes. In uniform motion problems, what the uniform refers to is the uniformity of the speed. There is no speeding up or slowing down in these problems. When you're going your 60 miles per hour for 2 hours, you're going that speed constantly for the whole 2 hours. Okay, the 1,600 miles a day or 1,600 miles in 5 days, that's a constant speed of 320 miles across the 5 days. So within the problems that are uniform motion problems, there's no speeding up or slowing down. And the motion will be governed by this equation, distance equals rate times time. Also, within the uniform motion problems, there are almost always two things. By things, those could be people who are walking or running or bicycling, to cars, to airplanes, to trains, or to boats doing something. The two boats, planes, trains, cars, people, whatever, could be moving toward each other. They could be moving away from each other. They could be moving in the same direction at two different speeds, either way. So two things: boats, planes, trains, cars, people, whatever, moving toward, away from each other in the same direction at two different speeds. Or it is one person, plane, boat, train, or whatever, doing two different things. So we might have one person who walks part of the way to school and then runs, or a boat that travels upstream, then downstream, or a person who walks to town and then back. One person, boat, plane, train, car, or whatever, doing two different things, or two boats, planes, trains, cars, whatever, doing something. So if each of those things, boats, planes, trains, cars, whatever, has a distance, rate, and time, or the one person, boat, plane, train, car, or whatever, has a distance, rate, and time for each part, that's 6 numbers. So a distance, rate, and time for each piece. So frequently with these problems, I like to organize the information in a table, and the table will have 2 rows and 3 columns. Across the top, we'll have distance equals rate times time. That's to help you remember the formula. And then the 2 rows are for the 2 parts of the problem, the 2 cars, or the person running and then walking, or whatever, as you will see. So there's some common elements that you'll see in each of the problems. So speaking of which, we should get started on a problem. So here, Nice long story. An express train and a local train leave Pittsburgh to travel to Washington, D.C. The express train can make the trip in 4 hours. The local train takes 5 hours for the trip. That's the same trip. The speed of the express train is 12 miles per hour than the speed of the local train. Finally, we get to the question, find the speed of both trains. So that's a lot. There's several sentences there. As I'd mentioned, I like to use a table to organize the information that we have. On this, we can solve the problem using a single variable. So I'm going to pick out the variable to be x. We'll make that the speed. Don't want to just say speed, right? Speed of which train, we should know. We're going to say that's the speed of the local train. Okay. So then in my table, I have distance equals rate times time. And then for the two rows of the table, we're going to have the local train and the express train. Each train has a distance, a rate, and a time. We're going to go through the story problem and figure out what stuff goes in which box. We'll start with our variable, which is the speed of the local train. Speed and rate here are the same, so x will go here, the local train's speed. Now let's see what else we can get out of it. It says that the speed of the express train is 12 miles per hour faster than the speed of the local train. So the express train, its speed will be x plus 12. Okay, and that takes care of that sentence. So we've kind of covered all of that. Got everything out of it that we can. The last sentence was just a question telling us what to do. What's next? The express train can make the trip in 4 hours. So that's the time for the express train. The local train takes 5 hours for the trip. So 5 hours for the trip. Okay, so now we can figure out the distance based on the fact that distance equals rate times time. So multiplying together the entries in the two following columns, we'll have 5x for the distance the local train travels, and then 4x plus 12 for the distance that the express train travels. Okay, so we've taken the express train can make the trip in 4 hours. The local train takes 4 hours for the trip. And again, the last piece is just the questions. So the piece that we haven't used is the beginning part. And it says an express train and a local train, are leaving the same place. They're leaving Pittsburgh to travel to Washington, D.C. And so both trains are making this same trip. And so their distances have to equal one another. Since they're taking the same trip, their distances have to match. So when you're working on these problems, once you've got the table filled out, you have to think about, well, what has to equal what? After all, an equation is a statement that two things are equal. And here, well, the rates are not the same. Their distances or times are not the same. What has to be the same? It's the distances, because they're making the same trip. Okay, luckily, the equation to solve is actually pretty easy. So we'll take the 4x from both sides. That will leave us an x of 48. So 48 was the speed of the local train. So the local goes 48 miles per hour. And then the express is 12 faster. So the express will go 48 plus 12, or 60 miles per hour. All right, and that's the end of that example. To just kind of recap, the first thing we did was recognize that it's a uniform motion problem. I drew out a table with distance, rate, and time for the columns. The two actors in our story are two trains, an express train and a local train. Then we went through the story problem, figured out what we were trying to find. In this case, it was the speed of both trains. I chose a variable to be one of them. And then we went through and picked out all the information from the problem and put it into the table. Once we had the table completed, either with story information or using the distance equals rate times time formula. Once we had the table completed, we figured out what has to equal what. That gave us an equation that we could solve. That takes us to the end of this example. We do have another one that we're going to do right now. So the story for this, Ashley goes to college in Minneapolis. That's 234 miles from her home in Sioux Falls. She wants her parents to bring her more winter clothes, so they decide to meet at a restaurant on the road between Minneapolis and Sioux Falls. Ashley and her parents both drove 2 hours to the restaurant. Ashley's average speed was 7 miles per hour faster than her parents' average speed. We're to find Ashley's and her parents' average speed. So pause the video, take a minute and set up a table and choose a variable, and then restart the video and see how you did. All right, so let's take a look. So I've started by making the table. The two kind of people in this problem are Ashley and her parents. So I'm going to make the first row be Ashley and the second row be the parents. Each column is distance equals rate times time. And then I need to go through and figure out what needs to go where. What we're trying to find is Ashley's speed and her parents' speed. So the two speeds again. We're told in this sentence that Ashley's speed is 7 miles per hour faster than her parents' speed. So we can choose the variable to be Ashley's speed or her parents' speed. I'm going to go with Ashley's because Ashley's mentioned first in the problem, but it doesn't matter which one you pick. So we're going to make X be Ashley's speed. Okay, and I'm going to definitely write that down so I remember. That will be Ashley's speed. The parents, she goes faster than her parents. So the parents go slower, and so that will be X minus 7. If you made the other choice and let X be the parent's speed, then you'd have X in the second row and an X plus 7 for Ashley. Okay. All right, so here it says Ashley goes to college in Minneapolis, 234 miles from her home in Sioux Falls. So the two places are 234 miles apart. We'll use that later. They meet at a restaurant in between. It says Ashley and her parents both drove 2 hours to the restaurant. So the time for both people or both sets of people is 2. Since distance equals rate times time, we'll have 2x under distance for Ashley, and we'll have 2x minus 7 for the parents. So there's that. So now we have to incorporate the 234 miles. And so we have Minneapolis and then we have Sioux Falls. And Ashley and her parents are going to meet at a restaurant in between. We don't know where in between, okay? It's not going to be exactly in between, right? Because Ashley drives faster, she's going to drive more of the trip, right? So it has to be closer to Sioux Falls, right? Because she's coming from Minneapolis, so it's going to have to meet a little closer to Sioux Falls. Anyway, it doesn't really matter. All we need to know really is that between Ashley and her parents, they're going to end up driving the whole 234 miles. She'll drive more of it than the parents, but that's okay. So the distance that Ashley drives plus the distance that the parents drive has to equal the total 234 miles. That's the real difference between this problem and the last one. In the last one, the two distances were equal. In this one, the times are equal, but the distances add up to something. Okay, so that's the setup. Again, the equation itself is not that bad to solve. And so let's go ahead and go through the details. So I've distributed to remove parentheses, then combine like terms. Now we'll add 14 to both sides. That's 248. Okay, and then I need to divide that by 4. So that will be 62. And the speed is in miles per hour. Okay, so Ashley goes 62 miles per hour. And then the parents 7 miles per hour less. So that will be 55 miles per hour. Okay, again, just to kind of look over it, we read and understood the problem. I used a table to organize the information. We picked out a variable to represent one of the things that we're trying to find, and fill in the table from the information in the problem, and then figure out what has to equal what, and then solve the resulting equation. Okay, let's try this again. All right, so Pierre and Monique leave their home in Portland. So they're leaving the same place, leaving their home in Portland at the same time. Pierre drives north on the turnpike, that's like a freeway, at a speed of 75 miles per hour, while Monique drives south at a speed of 68 miles per hour. We want to know how long it'll take for them to be 429 miles apart. So again, we're going to have distance equals rate times time. And our two players in this story are going to be Pierre and Monique. And they leave at the same time. Pierre goes 75 miles per hour. Monique goes 68. They leave at the same time, and we want to know how long it'll take for them to be 429 miles apart. So the time is going to be the same for both. So we'll have 75x for Pierre's distance, 68x for Monique's. So they leave home, and Pierre goes north, and Monique goes south. And we don't know how far exactly each one goes yet because we don't know x, but we do know that we want to know the total distance between the two to be 429 miles. Okay, so 75x plus 68x will equal 429. Okay, so this time the total distances traveled equaled 429 miles. So we want to combine like terms. And so that works out to be 143 x. And then let's divide through by the 143. Okay, and that's not going to come out even, and that's okay. So actually it does. I'm kind of surprised there. It looked like it totally looked like it was not going to. Divides, ends up being 3. Okay, so they drive for 3 hours. Okay, all right, and that will do it. Okay, on to our next example. Okay, and so this is one about a boat going upstream and downstream. All right, so it says Sean takes 45 minutes to drive her boat upstream from the dock to her favorite fishing spot. It takes her 30 minutes to drive the boat back downstream to the dock. The boat's speed going downstream is 4 miles per hour faster than its speed going upstream. Find the boat's upstream and downstream speeds. Okay, so as before, we're going to make a table. We're going to pick out a variable and try to figure out what has to equal what. So at this point, pause the video, try to set up as much as you can, then restart the video and see how you did. All right, this is what I've got so far. I made up the table, and the two parts of our story are upstream and downstream. And I've decided to choose the variable to be Sean's speed upstream. So that will go in the second box in the first row. And we're told that her speed going downstream is 4 miles per hour faster. Okay. And then what else? The other parts are about the times. And here we're going to need to be really careful about the times because both of the times are in minutes and our speeds are in miles per hour, or the offset between the two speeds is in miles per hour. So just as a reminder, and we discussed this before, if you have two rates, you need to make it so that the time units match. If you were to drive 60 miles per hour for 15 minutes, okay, we're not going to figure out your distance traveled by multiplying 60 by 15, right? So instead, you either need to figure out how many miles per minute you go, or you need to figure out what fraction of an hour 15 minutes is. And usually that's easier to go with, even if you don't like fractions, especially. It's going to be easier than figuring out the number of miles per minute. Okay, so 45 minutes is 3/4 of an hour, and 30 minutes is half an hour. So she goes upstream for 3/4 of an hour and downstream for half an hour. We've changed the time units to hours to match the fact that we're given 4 miles per hour faster as the offset between the two speeds. So now the distance upstream is 3/4 x. The distance downstream is a half x plus 4. So we've got the table filled out, and we have to think about what is equal to what. So she starts at her car, right? When she like gets out, gets in the boat, and then goes up to her fishing spot and then comes back. So I think it's fair to say that the distances traveled upstream and then back again are going to be the same. She's going to return to her starting place. So we will have 3/4 x equals 1/2 x plus 4. Okay, so the distances traveled have to match. She goes there and back to her starting point. So I'm going to multiply both sides of the equation by 4 just to clear the fractions out. Not a necessary step, but makes life easy. Okay, so 4 times 3/4 of an x is going to be 3x. A half times 4 will give us 2. Okay, we still have the parentheses to contend with, so let's distribute to remove the parentheses. And then we'll find pretty quickly that the x is 8. So her upstream speed is 8 miles per hour. And then it's 4 miles per hour faster downstream, so it'll be 12 miles per hour downstream. Okay, and that takes care of our boat example. Okay, we have one more to try. So you'll notice that all these problems look long. So when they're on a test or something, try not to be intimidated by them. There's a lot of writing. It just takes careful reading and processing in order to get the problem solved. But as you can see, there's kind of a theme to all of these. We end up setting up the information in the table. We pick out a variable. We read through the problem and the information in the table. Then we figure out what has to equal what and solve the corresponding equation. So let's try that here. All right, so the story here is we have this guy, Hamilton, who goes to Las Vegas, which is 255 miles from his house in Orange County. One day, his last time he went, he left the house at 2 o'clock, and the first part of the trip was through congested city freeways. At 4 o'clock, the traffic cleared, and he was able to go the rest of the way through the desert. 1.75 times as fast as he was going through the city. So he arrived at Las Vegas at 6:30 p.m. We want to know the speeds at which he was traveling during each part of the trip. So set up the usual table. I chose X to be the speed through the city because we're told that the desert speed is 1.75 times as fast as the city speed. And it just seemed easier to me to do the desert speed in terms of the city speed. All right, so what's new about this problem is that instead of giving like the amount of time for each thing, like 2 hours upstream, 2 hours downstream or whatever, we're given absolute clock times. And so we need to calculate the time elapsed. So the part through the city, he leaves at 2 o'clock and then the traffic clears at 4 o'clock. So the part where he's in the city is 2 hours. Between 2 p.m. and 4 p.m. he's driving through the city. Okay, then between 4 p.m. and 6:30 p.m., that's the part where he's driving through the desert. 4 p.m. to 6:30 p.m. is 2.5 hours. Okay, so we've turned this into a number of hours. Okay, so then finally the distances are equal to the rate times the time. Okay, so we filled out our table, and then the distance traveled is going to be his home to Orange County up to Las Vegas. Part of it was through the city, part of it was through the desert, but either way, it has to total that 255 miles. So the two distances traveled have to total, that is, add up to and equal the 255 miles. So the city distance plus the desert distance has to equal 255 miles. Okay, so then let me do a little calculating. So we need 2.5 times 1.75, and that's 4.375. Okay, we'll combine like terms. The setup on these is always kind of the more work. The rest of it is pretty straightforward. Okay, so that works out to be 40. Okay, I have to go back and remember what the X is. Good thing I wrote it down. X was the speed through the city. So he averaged 40 miles per hour through the city. And then 1.75 times that, which is going to be 70 in the desert. Okay, that takes us to the end of our look at uniform motion problems. Hopefully you feel pretty comfortable about it, but if not, let me know if you have any questions, and then have a great day.